Very good. Here, let's do a different example, all right? Oops. This time, there we are. This time, let's find the average value of a function of x. Let's find the average value of the potential energy in a harmonic oscillator potential for the state n equals 0. Remember that the n equals 0 state of a harmonic oscillator potential looks like a Gaussian function. Try to sketch it out here. Okay, and also remember that u of x is equal to 1/2 m omega naught squared times x squared. Okay? So we might imagine that even though the expectation value of x is probably 0, because this is a symmetric potential, symmetric about x equals 0, the expectation value of potential energy is not going to be 0, okay? But it's going to be larger. Well, let's see how this works. So, very good. Now, to solve this problem, we need to know the wave function in the lowest state. And we've written this down. Psi 0 is equal to a constant, C0, times e to the minus alpha x squared. And so far, we haven't needed this, but now we will. The constant C0 can be established by normalization, and it works out to be m omega naught divided by pi times h bar, okay? Quantity to the 1/4. And the quantity alpha is equal to m omega naught divided by 2 pi. I'm sorry, 2h bar. There we are, okay? So those are results we haven't needed up till now, but now I'm just going to write them down. Therefore, using this, the expectation value of the potential energy will be the integral over all possible values of position of u of x times psi 0 star times psi 0 dx. And then that will be, from u of x, it's 1/2 m omega naught squared times c0 squared times the integral of x squared e to the minus 2 alpha x squared dx. Okay? And just continuing, we can solve this integral and then write out our solution. Okay? So the next step would be to do a substitution. Like so, okay? And that's just to put our integral into a general form. Once we do that, you can show that the result will be, oh, I'm sorry, I wanted to, there we are. Please excuse me a second, there. After that substitution, the result will be 1/2 m omega 0 squared times c0 squared times 2 alpha to the power of minus 3/2 times the integral infinity to minus infinity of y squared e to the minus y squared dy. Okay? And finally, this is another one of the integrals that we wrote down at the beginning of the class. Let's just go look it up. Here it is. So this is root pi over 2. Sorry. We're scrolling around like this. Okay? And so finally, we can put in our results and simplify. So the expectation value of potential energy then is 1/2 m omega naught squared times C0 squared, which is m omega naught over pi h bar to the power of 1/2 times, from the next term, h bar over m omega naught to the power of 3/2, and then root pi over 2. Okay, looks kind of complicated, but some things cancel out. Okay, and oh yes, this pi cancels with that pi. And this works out to be 1/4 h bar omega naught. So the expectation value of potential energy for the lowest state of the harmonic oscillator potential is 1/4 h bar omega naught. So it's not zero at all. Whew. All right, just scrolling up here, okay? So anyway, that was a nice example of finding the expectation value of a function of x. And the average value of x, we can see that the average value of x squared is not zero, because since x squared only takes on positive values, it would be impossible for its average value to be zero, right? Something else that's kind of interesting, note that the total energy of the n equals 0 state of the harmonic oscillator is 1/2 h bar omega. And this is equal to potential energy plus kinetic energy. And that pretty much tells us right away that the average value of kinetic energy must also be 1/4 h bar omega naught, right? Because then they can add up to the correct total energy. Anyway, that's just an aside. Here, let's stop for a moment.